Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today, we're working on problem number 3.26. This is a computer problem, so we'll be moving over to the computer here pretty soon. I will go ahead and read the problem statement. A gas chromatograph, GC, is a device used to separate the components of a sample of a gas or liquid mixture and to provide a measure of the amount of each component in the sample. The output from the chromatographic analysis typically takes the form of a series of peaks on a strip chart recorder. See the preceding problem. Each peak corresponds to a specific component, and the area under the peak is proportional to the amount of that component in the sample. The number of moles is proportional to the proportionality constant times the peak area, where A sub I is the area of the peak corresponding to the ith species. The proportionality constants, Ki, are determined in separate calibration experiments in which known amounts of the components are injected into the GC sample port and the corresponding peak areas are measured. Part A, prepare a spreadsheet to calculate the composition of a mixture from a set of peak areas obtained from a chromatograph. The spreadsheet should appear as follows. Then they give us an example of what the spreadsheet should look like. You may use additional columns to store intermediate quantities in the calculation of the mass and mole fractions in the actual spreadsheet. The dashed lines would be replaced by numbers. Test your program on the data for 5 mixtures of methane, ethane, propane, and N-butane. The K values for these species are those given in the above table, and the measured peaks are given below. For example, the area of the methane peak for the first mixture is 3.6, the area of the ethane peak for the same mixture is 2.8, and so on. So let's go ahead and move over to the computer. Okay, so I've moved over to the computer here, and you'll see that I've set up the table that they gave to us. I've got the sample, each of the 5 samples that they asked. The species reoccur for each sample, and so I just have a column of species and they reoccur, as well as the molecular weights should be reoccurring for each species because those don't change with the species, as well as the proportionality constants. Then the thing that changes for each of our samples are the peak areas, and they gave those to us in the problem statement, and so those should change for each sample that we took, and I've got them all listed here. Okay, so it's our job to calculate what the mole fraction is. The function that we need for calculating the mole fraction is given here, where the mole fraction is equal to the number of moles of the species divided by the total number of moles. In order to calculate the number of moles in the sample, the problem statement gave this to us. It's the peak area times the proportionality constant. And in order to calculate the total number of moles, we would have to sum each product of the proportionality constant times the peak area of the certain species that we're working with. Now, Excel has a function for this called sum product. And so all we have to do is get the product of this component and divide it by the sum product of all the components. And it looks like this in Excel. So we take the proportionality constant times the peak area, and then this is divided by the sum product, which is each K value multiplied by the respective area for each term. And that, if we put the little dollar signs in here by pushing F4, then the sum product that we took won't change for each of these components, and then we can just drag down and we'll fill without formatting, and then we can just drag down each of those values. The sum of these mole fractions should sum to 1. In order to calculate the mass fraction of each species, we need to know how much mass of each component is in the sample, and then we need to know the total mass of the sample. In order to calculate the mass of each component, we need to multiply the molecular weight by the total number of moles of the component. In order to calculate the sample, the total sample mass, we do the sum product of the molecular weight times the number of moles of each component. Okay, so what that looks like in Excel, first we'll calculate the mass. The mass of the component is equal to the molecular weight multiplied by the number of moles of the component, which is the peak area times the proportionality constant. Then, in order to calculate the sum product of each component, we take the sum product of the molecular mass times the number of moles of each component, which is the proportionality constant times the peak area. And this is the mass fraction of each component. But we need to make sure that they're referencing the correct values here. So shift these values down. Alright, so this is the end of part A. We've filled out the whole table and we've changed the values so that they're corresponding to the correct values on our sheet for each peak area. Okay, now let's go ahead and do part B. Write a computer program, not a spreadsheet, to perform the same task. That is, calculate mole and mass fractions from measured chromatographic peak areas. The program should perform the following steps. Okay, so let's go ahead and change programs. Okay, so I finished programming the program that they asked for in part B. It does basically the same thing that we just did in our Excel, but instead we have to kind of manually input the data in just a slightly different way, and we'll do that later when we're testing our program. But right now we have our function defined here. It takes M in, that's the molecular weights of each species, K is the proportionality constant for each species, and A is an array of values for each sample and each species. So sample first, and then we'll do species. So in the first set of arrays, we'll have, for the first row, we have another array that contains all of the species values for A. So if we take the length of A, it will look at how many samples we took. If we look at the length of molecular weights, that will give us the number of species we have. Okay. Then we loop over the full number of samples, and then we loop over, and for each sample we loop over all of the species that we have. We'll calculate the sample number, we'll calculate the molar fraction, and then we'll calculate the mass fraction, and then we'll print these out, and we'll print them out for each sample that we have. And so then if we input all of our data correctly into M, K, and A, then these should give us the exact same values that we got in our Excel sheet. We finished inputting our data, and so we've input all of our data here, and now we can run our code on each of these variables input into our function that we wrote. What we should get is a printout that says sample, and then gives our sample, and then xi, which is our mole fraction, and Wi, which is our weight fraction, and then we'll spit out each of those values. Let's add a little bit of space in between our printed values so that when they print out it looks a little easier to read. Okay, let's go ahead and execute our code, and if we've done everything correctly, we should get all of the values spit out that are the same as in the Excel table that we made. Okay, so we were missing one more set of parentheses that we needed in array. So let's try and run that one more time. Great. Okay, so we've calculated each of our samples, we've calculated each of our mole fractions and each of our weight fractions here. And now we need to see if these match up with what we got. Alright, so I've overlaid our code output with our spreadsheet table here, and as you can see here, each of these values is the exact same as what we calculated in our table, only these are a little messier because they go out to however many digits this is. There are ways in Python that you can clean this up and make it look way better, make it even look like it came from a spreadsheet using other Python programs, languages, or not languages, but other modules that you can import. However, I thought I'd just keep it really simple and just manually input everything, and then that's because I know that people that are usually studying out of this book at this level are just barely starting to learn programming languages, and so I tried to keep it as simple as possible, but also accomplish all of the steps that it asked for. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you'd like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.